Hello, my name is Dominic Finelli, and this is my presentation for Physics 2211, Lab Number 2, Motion of a Falling Object. So, introduction. The goal of this lab is to compare the observed position of an object falling to the predicted movement of that same object based on a coded model. And there will be two coded models, one with just gravity and one that includes gravity and drag. This lab makes use of Newton's second law and gravity by comparing the movement of a falling hat using tracker with the model produced by the constructed code. Gravity, Newton's second law, and drag force. These three principles are imperative to this experiment, as the force of gravity and drag force are the main forces acting on the hat during its fall. And the momentum principle plus gravity and drag are used to construct the coded model. And these are the two formulas. This is the momentum principle, and then this is drag force. So here's a video of the hat falling in tracker. So as you can see, the tracker produces data that we can then pull into an Excel spreadsheet, which I have right here. This is the time versus the observed position, and you can produce a graph based on this. As you can see, drag is included in this, obviously, because it's the observed position. It's in real life, so it kind of starts off flatter, the velocity. This is position versus time, so the derivative starts off flatter and then slowly slopes downwards, which means that the velocity is smaller at the top and then gets bigger until it reaches terminal velocity. So for the coded model with just gravity, it's fairly simple. We just have to calculate the net force, which is down here, the negative mass of the ball times gravity times j hat, and then calculate the new velocity using velocity update, which is the momentum principle, ball velocity plus F net divided by the mass times delta t. Then we have to update the position with the new velocity. So ball position plus ball velocity times delta t. And then the clock just advances, and we get this graph. Obviously, there's no drag, so it's a much more balanced slope. And here is another video. So as you can see from the video, the velocity is the same because throughout the entire fall, because there's no drag, the only force acting on it is gravity. So for the coded model with gravity and drag, it's basically the same process to find the net force. However, we just have to include drag. And the drag makes it so that the hat does not gain velocity as fast as the drag force opposes gravity. So in order to add drag to the calculation, we simply just put the formula in, negative b. B is the coefficient, and then we do negative b times mag ball dot vel times 2 times the normal of ball dot vel. And then for F net, we just add the force of gravity and the force of drag. And then the rest of it is the same. Here's a video of that. So as you can see from the end of the video, the velocity was not the same the entire time. It was very slightly changed throughout the experiment, which is due to the drag force. So we put these all into a graph. You can see that with just gravity, it's completely off from the observed position. The model with gravity and drag is pretty close, but there are some discrepancies, which are probably just caused by messing with tracker, by the points in tracker. So which model predicts terminal velocity, which is when F net equals 0? So pretty much all of the models will predict terminal velocity. It just depends on the end of the graph. As you go farther down the graph, if time was much longer, you get to a point where the slope was the same, and that would be terminal velocity. And what if the object was thrown downwards? Would terminal velocity be the same or different? Terminal velocity would be the same because eventually the forces would balance out. The acceleration downwards would still be the same. It would be gravity, and drag would oppose it. The acceleration would just be the initial velocity would just be increased. Other than that, nothing would change. You'd still end up reaching a point where the slope is the same and terminal velocity is reached. That's the end of my presentation. Thank you very much.